Okay, nucleophilic acyl substitution, chapter 22 in your book. This video is mainly going to start with the background material. Okay, how do we name this stuff? What's the basics about them? In the next video, we'll start actually looking at these reactions, but we got to get the nomenclature and just the general concepts out of the way. So here we go. Some basic stuff. RC double bond O is called the acyl group. We've looked at some of these molecules. We'll be looking at them further. One that we haven't really discussed too much, we've actually dealt with it in lab, but we haven't discussed it too much, is the anhydride, where you have an R group, methyl, ethyl, whatever, carbonyl, O, carbonyl, and the R group again. So another functional group, the anhydride, to look at. Of course, we have our amides here. Here is a primary amide, secondary amide, tertiary amide. Note, just like amines, primary, secondary, tertiary amides depend on how many things other than hydrogen are bonded to the nitrogen. If it's 3 hydrogens, it's ammonia. If you've got just this carbonyl and 2 hydrogens, it's a primary amide because the nitrogen is bonded to 1 carbon. Here the nitrogen is bonded to the R group and the carbonyl, nitrogen bonded to 2 carbons, secondary amide, nitrogen bonded to 3 carbons, tertiary amide. Esters are part of these RCOZ compounds that we're going to be dealing with. Note, for doing nucleophilic acyl substitution reactions, we're looking at RCOZs, not aldehydes and ketones. A cyclic ester is called a lactone. And note, an ester has to have a carbonyl carbon bonded to another oxygen to have an ester, and that oxygen bonded to a carbon, an R group. It just so happens the R group that this oxygen is bonded to finds its way through a ring back to the carbonyl carbon. And we count the other way, though, to tell us how many carbons in between the carbonyl carbon and the oxygen. And so we note that here's the carbonyl carbon. The one right next door is alpha to the carbonyl, then beta to the carbonyl, then gamma to the carbonyl. This gamma carbon is bonded to this oxygen, so we call this a gamma lactone. If note you have a 6-membered ring lactone here, alpha, beta, gamma, delta, this is a delta lactone. All right. Note a cyclic amide is called a lactam, as an amide lactam. So this would be a alpha, beta, gamma, delta. This is a delta lactam. And note it is a tertiary delta lactam. If you have a lactam, note you can only have secondary or tertiary. This is either a hydrogen or a carbon bonded to this nitrogen, so either secondary or tertiary. Nitriles, we have not talked about nitriles too much. We kind of throw them in here because they tend to do very, very similar reactions as amides do, because we have an R group, a carbon, and that carbon has 3 bonds to electronegative atoms. 2 bonds to an electronegative oxygen, 1 bond to electronegative nitrogen here. All of our RCOZs, carbonyl, 2 bonds to an electronegative oxygen, 1 bond to our electronegative Z, a chlorine, an oxygen, or something like that. Nitriles, here's our carbon. It's 3 bonds to a nitrogen, 3 bonds to a more electronegative nitrogen. That is the similarity between nitriles and our RCOZs. So we tend to lump nitrile chemistry in with our RCOZs because we're going to see some fairly similar type of reactions. All right. Note all these RCOZs have resonance forms because most of our Zs are either oxygen or nitrogen or chlorine, and they've got a lone pair on them. So we have these resonance forms here that gives the Z just a little bit of positive charge through resonance. The carbonyl gets a little positive charge. The oxygen gets a little negative charge. The more basic Z is, the more it can donate that electron pair, the more these resonance forms, this resonance form here, comes into being, the more it contributes to the resonance hybrid. Note, if the more basic Z is, the more willing it is to donate the electron pair, the more this resonance form contributes to the resonance hybrid, that means it's tougher to get rid of that Z, because we want to get rid of these groups as, and we've got a positive charge on here, and it's just a positive charge thing. It's just tougher to get rid of it. All right. Let's look at the basicity then of the leaving group. The weakest base of our leaving group would be chloride ion, because if you did the reaction and you have your acyl group here and you did our substitution, recall that Z is the leaving group, and it's going to leave carrying those 2 electrons with it, so it'll leave as Z minus. So if you had an acid chloride, chloride is a very weak base. Makes it a very good leaving group. The anhydride here is the next weakest base. It is a decent leaving group. Hydroxide we know is a poor leaving group, strong base. Alkoxide is about the same, poor leaving group, strong base. NH2 is a very strong base, NH2 minus, therefore it's the worst leaving group. What that means then is our acid chloride, it has the best leaving group. It is our most reactive RCOZ. Anhydrides, when an anhydride leaves, note, here the leaving group was Cl. The acyl group RC double bond O stays, the Cl leaves. With an anhydride, same thing. One of the RC double bond O stays, the rest OC double bond OR leaves. So this is our leaving group. And just for example, if this was a CH3 here, our leaving group would be acetate ion. Acetate ion is a fairly weak base. It's a conjugate base of acetic acid. Acetic acid is a weak acid, therefore acetate ion is a weak base. Weak base, good leaving group. Makes anhydrides very reactive. We've already talked about these guys. Ester is not very reactive because poor leaving group. Carboxylic acid is not very reactive. We're going to open up a can of worms with these, with that acidic hydrogen there later. And amides are the most stable. They are the least reactive of the RCOZ that we're going to look at that have the carbonyls in there, our acyl groups. All right, well, what we have not discussed too much is how do we name these compounds? How do we name RCOZs? Well, the thing to remember is RCOZs are called carboxylic acid derivatives. And we're going to name them basically based on a carboxylic acid. So you're going to pretend it is a carboxylic acid, name it as if it was a carboxylic acid, and then change that name to fit what it really is. Okay, what does that mean? It's easier to just show you. RC double bond OCl. This is an acid chloride or acyl chloride. For example, what is the name of our CH3 C double bond OCl? Well, first, what if instead of a Cl here, this was an OH? What if we took off the Cl, put an OH to make it the carboxylic acid? First, you name it as the carboxylic acid. This would be acetic acid. So, yeah, you start by naming it as if it's a carboxylic acid. It would have been acetic acid. And then you say, okay, but it's not a carboxylic acid. It's not acetic acid. We've got a chloride right here. So you drop the ic acid from acetic acid and add ill chloride. So we're going to drop ic acid and we're going to add ill chloride. So this is acetyl chloride. Yeah, kind of weird. You look at the molecule, pretend it's a carboxylic acid, name it as a carboxylic acid, then change the name, drop ic acid, and add ill chloride. All right. When you have a ring in your system, we know this is a cyclohexane ring, and so what we're going to do, this group is off the cyclohexane ring, so we're going to call this the carboxylic acid becomes a carbonyl chloride. So if this was a carboxylic acid, it would be cyclohexane carboxylic acid. It becomes cyclohexane carbonyl chloride. All right. So what if we were naming this one down here? Well, if this were an OH, it would be 1,2,2-methyl, 2-methyl-butanoic acid. We drop the ic acid, but note we keep the O. This was 2-methyl-butanoic acid. We only drop ic acid. We keep the O in there, so this becomes 2-methyl-butanoyl chloride. And some people say butanoyl. Some people say butanoyl chloride. I don't know, whichever works for you. But that's how we name our acid chlorides. Pretend it's a carboxylic acid and name it as a carboxylic acid. Drop ic acid, add ill chloride. Anhydrides. There's two types. These two R groups could be the same or they could be different. If these two R groups are the same, we call that a symmetrical anhydride. And it's the same thing. We'd say, okay, what if instead of an anhydride, it was a carboxylic acid? For example, let's look at this. We have CH3, C double bond O, O, C double bond O, CH3. What if we had this acyl group and that was it? And what if this acyl group was part of a carboxylic acid? Well, we've already seen that. If this is a carboxylic acid, that would be acetic acid. And so we're going to change from acetic acid. We're just going to drop the word acid and add anhydride. So with this symmetrical anhydride, acetic acid, because this is the acid group, becomes acetic anhydride. If you have a mixed, a unsymmetrical anhydride, we know that, okay, this is our acid group, so that would have been acetic. This is our well, if this were an acid, this would be benzoic acid. So this becomes acetic benzoic anhydride because we do it alphabetically. So yeah, you look at the two halves of the molecule. If this were an acid, this part here were an acid, it would be acetic acid. So we've got acetic. If this part here were an acid, it would be benzoic acid. So we've got benzoic, acetic, benzoic anhydride. Cool. All right, esters. How do we name esters? The way we're going to name it is we're going to look at the RC double bond O, our acyl group. We've got this other oxygen here, and we've got an R prime, an alkyl group attached to this oxygen. You're going to name the alkyl group first, followed by the acyl group, but instead of ic acid, if it was a carboxylic acid, we're going to add 8. Okay, let's look at this. Easy part. If we've got CH3, C double bond O, O, CH2, CH3, we can see that bond to this oxygen is an ethyl group. That's ethyl. Got it. Let's look at our acyl group. What if this were part of a carboxylic acid? Well, it would have been acetic acid if this were part of a carboxylic acid. We're going to drop ic acid and just add 8. So the first thing we name is the alkyl group, ethyl. Acetic acid without ic acid and adding 8 is ACETATE, ACETATE, acetate. So this is ethyl acetate. And that's how we name esters. Whew. Amides. Just like before, we're going to name it as if it's a carboxylic acid, but then we're going to replace ic acid. Note, or would we replace the oic acid or the illic acid just with the word amide? So, yeah. So what this is, if this part right here were a carboxylic acid, if this were a carboxylic acid, it would be benzoic acid. We're going to replace oic acid with the word amide. So this was benzoic acid becomes benzamide. Benzamide or benzamide. If this would have been acetic acid right here, so it becomes acetamide or acetamide or acetamide. or however you want to pronounce it. As long as if you've heard someone with a PhD in chemistry pronounce it, then it's okay. All right. Cool. But what if this were a secondary or tertiary amine? Well, then we need to name the groups coming off of this nitrogen as alkyl groups, but we also need to indicate they're coming off that nitrogen. So if you had an ethyl group on your acetamide, note, acetic acid becomes acid. There's an amide, so it's acetamide, but there's an ethyl group on that nitrogen. This is N-ethyl acetamide. Note right here, if there were two CH2s on this would be N,N-dimethylbenzamide. Benzoic acid becomes benzamide, N,N-dimethyl. Cool. All right. Nitriles. Let's name some nitriles here. Nitriles are named as alkane derivatives. Just standard IUPAC name. This carbon is part of the longest chain, and so we name it with just like before with alcohols. This carbon has to be part of the longest chain. If there's another longer chain, doesn't matter. This carbon's got to be carbon in there. It's probably carbon number 1. And so if we had CH3, CH2, C triple bond N, that's 1, 2, 3 carbons in a row. So this would be propane nitrile. We just name the alkane, 3 carbons in alkane, propane, add the word nitrile at the end. Gotta love that, IUPAC. Propane nitrile. Of course, that's IUPAC. The common name is just like before. We named it just like we had named the acid, but add O-nitrile. So note, if CH3 single bond C triple bond N, this CH3C would be the acid group, and so it would have been acetic acid. We drop ic acid and add O-nitrile, acetonitrile. Note, if our cyano group is a substituent on the ring, or it's just you just want to consider it a branch, it's the cyano group. So if this is cyclohexane, we'll get to it later, double bond cyclohexanone. We've got a cyano group 2 on the second carbon, so this would be 2-cyanocyclohexanone. All right. And just quickly, some spectroscopic properties. Recall carbonyls have a big carbon double bond oxygen stretch from 1600, usually 1650 to 1850. I haven't seen very many below 1650. 1650 to 1850 wave numbers. Amides, we've got our NH stretches at 32 to 3400 wave numbers. NH bending is at 1640 wave numbers. Nitriles, they're nice. C triple bond N comes in what I call no man's land, in between 2000 and 2700 wave numbers. There's hardly anything. So if you got a nice sharp peak in there, that's either a carbon-carbon triple bond or a carbon-nitrogen triple bond. So nitriles at about 2250, fairly easy to diagnose. Note, the higher the basicity of Z, the more delocalized the carbon double bond oxygen is, the lower the frequency, which means very weakly basic chlorides come at about, the carbonyl stretch comes about 1800. Amides come about 1630 to 1680 or so in the IR. NMR, recall that a hydrogen on a carbon next to a carbonyl comes between 2 to 2.5 ppm. In the proton NMR, carbon 13 NMR, carbonyls come between 160 to 180 ppm. Yeah, cool. So, a few other things. This hydrogen, this on an amide, comes with around 7.5 to 8.5 ppm. Take that with a little grain of salt there, because it's on nitrogen. Weird things can happen. And the carbon of a nitrile comes at about 150 to 115 to 120 ppm in the carbon 13. All right. So that does it for this video today. In the next video, we will start looking at our reactions. We're going to look at the general reactions first and then look specifically at the reactions of each different RCOZ compound.